Good morning, students. In this video, we're going to discuss about asynchronous RAM. Under that, we're going to see about two different types of memories, static memories and dynamic memories. Okay, so we are going to classify the static memories and dynamic memories in the random access memory. So we are going to say that a static random access memory, dynamic random access memory. Memories that consist of a circuit capable of retaining their stage as long as power is going to be applied are known as static memories. So in generally, if you're going to see about that, static RAM consists of a circuit that are capable of retaining their states, and it's going to be a volatile memories because their content are lost when power is going to get interrupted. So access time of a static RAM are in the range of few nanoseconds. However, its cost is going to be usually high. The dynamic random access memory do not retain their state indefinitely, so that its content must be periodically refreshed, and the content may be refreshed while accessing them for reading. This is the general introduction about static RAMs and dynamic RAMs. Let us see about a static memories in detail. So static RAM can be accessed very quickly with a few nanoseconds. So let us see about the types of static RAM. So in general, if you're going to see about that, this SRAM cell, two inverters are cross connected. So which is going to be T1 and T2 are going to be cross connected, acting as a switch that can be opened or closed under a control of the word line, the green color line which have been given in the horizontal bottom, that is going to be called as a word line. When the word line is at a ground level, the transistors are turned off and the latch retains its state. For example, let us assume that the cell is in a state 1 if the logic value at the point x is going to be 1 and y is going to be 0. The state is maintained as long as the signal of the word line is going to be under the ground level. Okay, let us discuss about the operation which is going to be present over there. First, we can see about the read operation. In order to read the state of the SRAM cell, the word line is activated to close the switches T1 and T2. If the cell is in state 1, the signal on the line B is high and the B dash on the bit length line is going to be 0. The B naught will be 0, B is going to be high. If the cell is in the state 1, it's going to be the situation. The opposite is true if the cell is in the state 0. If the cell is going to be having the state 0, then B is going to be 0 and B dash is going to be 1. There is nothing but high. Thus, the B and B dash are complements of each other. Sense bar write circuit at the end of the bit lines monitors the state of B and B dash and sets the output accordingly. If the operation is going to be a write operation, the state of the cell is set by placing the appropriate value on the bit line B and its complement on the B dash and then activating the word line. Okay, this forces the cell into the corresponding state. The required signal on this bit lines are generated by sense bar write circuit. Such a way it's going to do its operation. Okay, once again I am going to say that if the word length is going to be, the word line is going to be initiated first, so it's going to be a read operation. For the write operation, the bit length line is going to be get activated and we have to place the bit in B and the complement of the data is going to be placed in the B dash. So it's going to do the operation of write operation. Such a way it's going to do the operation of read and write operation in the static random access cell. Let us see about an example of complementary metal oxide semiconductor cell. A CMOS a realization of the cell which have been shown in the figure over here. Here the transistor pair T3 and T5 and T4 and T6 which forms the inverter in the latch. Okay, so the state of the cell is read or written as explained earlier. For example, in state 1, the voltage at the point X is maintained high and high by having the transistor T3 and T6 on, while T4 and T5 are off. Okay, thus what happens if T1 and T2 are turned on, which closes bit line B dash and B dash will have high and low voltage signal respectively. So the power supply V supply, which is going to be, generally we can take that it's going to be a 5 volt in older CMOS, which is going to be 3.3 volt also going to be there. Sorry, older it's going to be 5. In new SRAM cells it's going to be 3.3 volt. So note that now the continuous power is going to be needed for the cell to retain its state. If the power is interrupted, the cell content will be lost. When power is restored, the latch will settle into a stable state. So, but it is not necessarily be the same state the cell was in before the interruption. Hence, SRAM are said to be volatile memories because their content were lost when the power is going to be interrupted. So, a major advantage of the CMOS SRAM is their very low power consumption because current flows in the cell only when the cell is going to be being accessed. Otherwise, the transistor T1 and T2 and one transistor in each inverter are going to be turned off, either T3 or T6 or T5 or T4. So which ensures that there is no active path between the V supply and ground, so that the static random access memory can be accessed very quickly. Access time of just a few nanoseconds are found in commercial available chips, so that the static random access memory are used in applications where speed is of critical concern. Okay, there's no such concern is going to be there. So in such a critical concern, we are going to use the SRAM, static dynamic random access memories.